Hello! We will conclude the module on duality by using it to give a nice proof that a certificate of infeasibility always exists if the LP is infeasible. This is called Farkas' lemma, and it states that, given a matrix A and a vector B, exactly one of the following two conditions holds. Either there exists vector x such that ax is equal to b and x is non-negative, or there exists a vector y such that A transpose y is at least 0 and y transpose b is strictly less than 0. The first condition means that the system of the constraints in standard equality form has a feasible solution. The second condition means that a certificate of infeasibility exists for this system. So either our LP is feasible or a certificate of infeasibility exists. We now give the proof of this lemma. We first prove that the two conditions cannot hold simultaneously. Suppose otherwise, so we do have vectors x and y that satisfy all of these conditions. Then y transpose b is equal to y transpose ax. That's because ax is equal to b. If we look at the right-hand side of this equation, y transpose A is equal to A transpose Y all transpose, which is non-negative. And also x is non-negative. So we get that y transpose AX is at least 0. However, the left-hand side y transpose B is assumed to be strictly less than 0. So that is a contradiction. So it is not possible that both conditions are true at the same time. We now prove that one of them must be true. A way to prove this OR condition is assume that the first condition is false and prove that the second condition holds. So we will assume that our system is infeasible and try to find a certificate of infeasibility. We will consider the LP that is max 0 transpose x, ax is equal to b, x is at least 0. This is infeasible because we assume that the first condition fails. So the dual is either infeasible or unbounded. So what is the dual of this LP? The dual of this LP is min B transpose Y subject to A transpose Y is at least 0. Can you determine the outcome of this dual? We see that this is not infeasible. That is because the 0 vector is a feasible solution. So the dual is unbounded. This means that there is a series of feasible solutions to the dual whose objective values approach negative infinity. In particular, there must exist some solution with negative objective value. For such a solution Y, A transpose Y is at least 0, and B transpose Y is strictly less than 0. This gives us our certificate of infeasibility, and it proves the second condition. And that concludes the proof of Farkas' lemma. We now give a geometric interpretation of this lemma. We will look at this example of a system. We now rewrite this system as a linear combination of the column vectors of the coefficient matrix. So 21x1 plus 1 minus 3x2, etc. is equal to phi 3. Now, if there exists a feasible solution, then x is non-negative. So phi 3 is in the cone of the column vectors of A. We can draw the column vectors of A here, and this region is in the cone generated by these column vectors. So if the right-hand side vector is in this cone, then the system is feasible. but our particular vector phi 3 is not in this cone. So no feasible solutions exist. By Farkas' lemma, there exists a certificate of infeasibility y. In this case, 1 minus 2 is one such certificate. We now consider the line with normal vector 1 minus 2 going through the origin. We see that all column vectors are on one side of the line. A transpose y at least 0 implies that AI transpose y is at least 0 for each column AI. So these column vectors are on the non-negative side of the line. But the right-hand side vector is on the opposite side of the line. The dot product B transpose Y is negative. So it is impossible for the right-hand side to be in the cone. Hence, it is infeasible. In general, Y is a vector that defines a separating hyperplane, with column vectors of A on one side of the hyperplane and B on the other side. So Y shows that the system is infeasible. And that concludes our discussion on Farkas' lemma.